Sorry. Okay. So Mark, why don't you take it away, sir, for a bit?
Okay. Do you see the pallet in the warehouse? I'm sharing the screen. Do you see it? Do you see a black box? Okay. So this arrived. This was the only electromagnet that we could find that people were actually responding to emails, and it weighs over a ton. So we needed the forklift to move it in. Oops. Let me see. Okay, there we go. This is how it was packaged. That is the space. Now these two plastic acrylic things were actually easily removable. These are those double-sided threaded rods that you can just turn them around a little bit to expand it in and out. And I'll show you what that was in a second. These are the casters that came with it. We had to replace those. They're garbage. It also came with a Hall effect sensor, although there is no tool to attach it to. So, now this is the acrylic pieces. It had these little coils in them with wires going to each coil, and still unsure what this was for or what it was used for. But you notice that the connections over here are all brass. So they were using non-ferrous materials for whatever it was they were doing. Not really sure what this was used for, either detection or modulation of the magnetic field. And that is the connector port at the end of it. This is the space. So we have like a 2-inch space between the plates, and the plate's diameter over here is 3.5 inches. So it's a pretty sizable space. I hooked it up to our KEPCO power supply, which is the bottom one over here. And I used this Gauss meter, which was recommended at APEC, at the last APEC conference. It's the Alpha Labs one. We also got the zero Gauss chamber to calibrate it. The magnetic field is pretty homogeneous. It's not like 100% perfect, but it is a lot tighter than anything we've achieved to date. And here we're just lifting it up and putting on the new casters. And I'll just get a couple pictures, and there it is, sitting right there in our lab next to the Marx generator. So that's just an update from the lab about the electromagnet. This thing is very heavy. Pushing it around is kind of dangerous because, like, once you get it moving, it has as much momentum as a pickup truck. Really, it's if you don't push it in the right direction where you want it to go, it'll smash into something and crush it, even going like 2 miles an hour. Really powerful. Okay, that's it. Any questions, any comments on what that little coil thing was? I guess not. Oh, Todd wrote in the comments, those are pickup coils. Well, wouldn't it only be able to pick up a changing magnetic field? Because
well, I think are we in open discussion now, Mark?
Oh, to pick up from the signal from the sample. Okay, I get what he's saying. Yeah, it's for NMR then, right? I'm reading off of Todd's comments in the chat.
Oh, okay.
Yeah, he said, yeah, that would be used for NMR for the to read the signal coming off the sample. Okay, that actually makes a lot more sense. Okay, I guess we're ready to go to open discussion then.
Okay, let's do it, guys. Let's do it. So we have had a big day today. Lots of coffee and lots of bathroom trips. I should apologize for that one that I didn't get back from in time. So yeah, I would say anybody who wants to join in, open discussion time.
How much Tesla we can get out of it. With our power supply, we're able to get 0.86 Tesla. And I think Thomas Anderson has a question for SPFL.
Yeah.
Yeah.
Yeah, and SPFL is still here. So I would say go for it, guys. Thomas, go for it.
I wasn't watching the chat, so if anyone had questions, feel free.
Oh no, it's my fault too. Yeah, I would say just let's just do open discussion now, guys.
I wanted to ask more about talk more about squeeze states and how that relates to polaritons.
Well, polaritons are one of many nonlinear materials. Well, so polaritons arise in nonlinear materials and allow very strong light matter interactions. So basically, if you have a material with very strong light matter interactions and nonlinear interactions as well, then you can get various quantum entanglement in the light. So 2 photon states, 3 photon states, whatever else. It's all about the, like, I mean, I've talked to you in the past about like parametric amplification. If you can make parametric, like if you can drive a parametric oscillator at twice the resonant frequency, that is the most efficient way to produce squeeze states I know of. You can do it at 3 times or n times the frequency, but you're going to have weirder entangled states and produce less efficiently. But I assume those sorts of states have uses. So it's really, that is a type of materials that have polaritons in them interact strongly with the light and allow you to squeeze it. The polariton itself is just a means to getting that nonlinear coupling in this specific instance. I mean, you can use polaritons for a ton of other things too. You can use them for the photocatalytic water splitting that I mentioned with graphitic carbon nitride. You just have an exciton and then you add some graphene layers to trap it as a polariton with a longer lifetime until it has a chance to split an atom of water, stuff like that. There's other uses, but it all involving light matter coupling.
How do squeeze states interact with gravitons and gravity?
A squeeze state in this case would be a superset of the graviton, which unifies it with the photon. So the graviton that we're searching for in physics is in this case, in this model, what we think of as a graviton is the squeezed vacuum state without any necessarily like photon amplitude. So if you took some sort of squeeze state and you canceled out all of the net electric and magnetic fields, what you'd be left with is a wave of shot noise. And that is equivalent to the graviton in this case. Oh, and if anyone has other questions, I'll put my email in the chat.
Victor Wag has a super chat for $35 in our live chat. He said, thank you to the mystery guest for an incredible introduction to the layperson like himself. Extremely valuable. Yes, I agree. And, you know, hopefully providing that barrier or that bridge between, you know, these really smart guys in the academic world and some of the experts that come on here and the layperson, because breaking this down to ways that we can all understand it and sort of work with it in different ways. That's hopefully what goes on here. And thank you for that.
I was just going to say one thing I wanted to interject was your discussion about economy and whatnot. I think the problem is that most people want to jump straight to that Star Trek future and they don't want to do the legwork to get to it. But every time I talk to groups that are doing research and work in the background, I always hear we need, you know, this equipment, or, you know, it would be great if we could get somebody to give us that equipment, or if we had more money. And I think if they would spend a little bit of time focusing on that aspect of it to kind of squash that bug before they get further into, you know, their work, it would probably make their future work a lot easier. So, I mean, it doesn't seem like it's, you know, a difficult thing to overcome if you're willing to spend a little bit of time just basically investigating it, you know, whether it's like understanding how money works, or, you know, the process of like figuring out how to determine what is valuable to some other people so that you can then provide them with something that they'd be happy to have, and you know, the things that they have that you need for your research, they're more than willing to help you out with. You know, once you have all that, then, you know, it's just basically a no-brainer to step forward. So unfortunately, the people that are so focused on the economy are usually not, they don't care about the science itself, so they're too busy ripping other people off, like the guy who was building the Slayer exciter copies, and didn't seem to want to give any credit to the guy that what is it, G. Bluer, about the whole thing, I guess, because he was afraid it would somehow affect his financial value or something. But people weren't buying those kits with the little Tesla coil and whatnot because of his, you know, them thinking that he invented or created it. They just wanted the tool. They were very interested in the actual tool itself. So, you know, it could have been something where he could have even maybe worked out a mutually beneficial system between him and G. Bluer, and the two of them could have basically kind of like, you know, got others that were more interested in just having a job to do the legwork, to put what they've got together, and then be able to basically push forward with their own works if that's what they were trying to do. Which I think, you know, Bluer is just more interested in electrical engineering and electronic engineering, and, you know, designing and creating things. He wasn't really worried about making money, so that's why he wasn't the first person to try to sell something off of that Slayer exciter design. So the manufacturing, though, I'll add to the economy thing, that is a big part of the reason why I put more of my time toward developing that kind of replicator level 3D printing upgrade, I guess, series of components for the technology to try to kind of cut the legs off of that problem completely. So that way it doesn't have to be focused on anymore. We can really get on to trying to, you know, test all these theories that people have thrown out there, or you know, new theories that people might have, or modifications to them where they see that maybe they could improve upon the design once they have done their, you know, their legwork of doing the testing to find something that actually has some sort of result they can measure. So of course it requires basically combining three pieces of technology. You've got to have the ability to refine or recycle to produce raw material, which you mentioned something about a spiral system that uses density for separation.
Yeah, spiral separators. They're used to mine monazite in China right now, and other things as well, I suppose.
Right. Well, and if you have like a, say, like a two laser system where one causes a chemical reaction, say to make like copper into copper oxide, but the other laser bounces off the copper, but it will ablate the copper oxide, you can now make sure that all of the copper oxide particles coming off are as small as, like, you know, you can physically produce because of the waveform of the two frequencies, so that they're very easy to work with. Then a little tiny bit of UV light and you can deoxidize that copper and cause the copper to collapse to form a solid copper mass, and just spread out layers of that powder back and forth while you know, laze over the surface, or run a, you know, a DLP system to reflect a high-powered laser where you change the shape of the beam itself with the little mirrors in the DLP system, and, you know, build up your solid copper component. So you know,
like this is a very long discussion and there's a lot of particulars, but one thing that's important to note about copper is there's only about 1 kilogram of copper per person on Earth. So for a realistic situation, you're probably going to have to rely on aluminum, because it's so plentiful everywhere and the supply of it cannot be blocked. That's the idea.
Right, but you need to be aware too that aluminum is one of those things that, even though it's like the third most abundant element that's in the crust of the earth, up until even Napoleon's era, because of the lack of knowledge on how to basically use energy to split and process the material to get at the raw aluminum, he had a whole group of dignitaries that showed up where only the wealthiest and most important got to eat with aluminum silverware. The rest had to just make do with solid gold. Yet now we can buy it for 35 cents a pound.
It's a little ironic though, because aluminum's not very good for your brain health long term. But anyway,
yeah, aluminum metal. There is something else to that though too. You know about zeolites, correct?
Yeah, but before you go on to zeolites, if you saw one of the things I mentioned, those aluminum chloride urea batteries, can isolate aluminum room temperature, and aluminum chloride urea is not super toxic or anything relative to some of the other processes that would be used with like molten cryolite and high temperatures and crazy things. But yeah, aluminum chloride urea, inexpensive, not super toxic.
Seems like the chloride would have a
very
pretty
high,
strong bond on the
very
aluminum.
high, very high thermodynamic efficiency. I think they were able to isolate aluminum. They were able to charge the battery with 99.7% coulombic efficiency. So that is how you would basically take aluminum hydroxide and put it in hydrochloric acid and then mix it with urea and then electrolyze it at a couple of volts, and then you have your aluminum. That easy. Like
Right.
these things are things we're working on in detail in various other groups, and we definitely need these solutions for the future of humanity. But yeah, it's not propulsion, I guess. So sorry for squeezing that into a propulsion conference.
Right.
But yeah, aluminum batteries, not only will they be a good replacement for lithium batteries, but then you have a simple, easy way of getting aluminum.
It might be easier to charge and discharge those too, since aluminum is amphoteric. So it can
Especially
act
under
as an
aluminum.
acid or a base. It doesn't matter.
Mhm.
What matters is what it's interacting with. So
Yep, nail on the head right there. Good stuff. Any other questions? I mean, people can email me too, but
you should maybe I don't know if there's any source already where they talk about your you were talking about urea to make graphitic carbon nitride through, I'm assuming you're talking about the thermal decomposition process.
correct.
Maybe some resources so people can basically avoid having to reinvent the wheel if it's something that's already been accomplished, like Robert Murray Smith was doing with was it silicon carbide powder to act as a microwave to thermal, basically using it to make a thermal emitter from a microwave emission. So you use a microwave oven to basically turn urea inside of a small vestibule into I guess he got like 30 or 40 grams worth of graphitic carbon nitride out of that. So
Basically, the only process you're going to want to use for photocatalytic water splitting, at least, is under ionic salts, specifically because the patent for that doesn't cover potassium chloride, lithium chloride salts, and then also just under a molten chloride salt, the crystalline structure is way better. The semiconductor, the band gap is way better and tunable. And then on top of that, ideally what you want to do for photocatalytic water splitting, and I don't understand why people haven't done this. You want to do photocatalytic water splitting at high temperature, high pressure, because then you get the lowest energy to split the water, and also you get the largest adsorption of.
I seem to see a common misconception of the photocatalytic cracking of water. It's not photocatalytic cracking of water. The water is cracking naturally on its own because of the catalytic reaction of the material. It's the photons that break the material free so that more water can get to the sites. Kind of like with the zeolites, where basically the site is so reactive, it'll tear other molecules apart in order to kind of fill its void, to make it's like a bunch of little cookie cutters that fill themselves up with these different components because of their electrostatic attraction and the size of the site. And then you got to figure out how to get those chemicals out without destroying them. So the photons make a very good way to basically push the material out. It was something that I wasn't, I was basically looking into the concept of using, because that's basically, you're using carbon to essentially cock block the nitrogen from making a permanent bond with either the hydrogen or the oxygen, but its energetic state through the neutral conductive state of the carbon allows it to transmit between the two, so that it can still reach through it electrostatically to pull the water apart. And that way it only takes photons to just knock it loose from the carbon. If you add a base along with the acid to make a hybrid, you wouldn't need the photons, because the vibrational energy of the heat itself would cause the displacement constantly because of those two electrostatic states constantly charging. And this may be happening naturally in the Earth's crust, coming up out of the ground and anything that's in the ocean would start cracking water to release oxygen into the air,
But
maybe
what-
providing the
so-
reason why there's oxygen and not the plants themselves, since after they die, they release all that carbon dioxide back into the air.
Not necessarily, but also if that were happening, wouldn't we already be out of hydrogen? Like there would be a very different equilibrium of hydrogen on the surface of the Earth if there were that much water.
If it were a consistent process that the material isn't destroyed, so it has to be constantly being replaced by geological formations of like the tectonic plates moving across each other and whatnot, and the pressure and the heat necessary to create them in the ground. On the other hand, though, if you take table salt and add it to that solution system, it'll destroy your photocatalytic cracker, because the chlorine will create a stronger effect on the carbon and break it free of the nitrogen, and then you end up with exposed nitrogen. The sodium reacts with it, damaging it too. So you need a perfect interlocking system in an equilibrium of water that doesn't have any contaminants that could basically sabotage your components. The same way zeolites have to be protected from sulfur whenever you're breaking down and reforming the compounds they get from distilling oil. So if there's a lot of sulfur, that's what they call sour oil, because it destroys their zeolites, and then they have to go out and spend more energy to make more of them, and they have to waste some of the material in order to get the patterning on the zeolites that they're making too. So it can be pretty wasteful because of that, just because of that sulfur, because they didn't get rid of it first. So in nature, I would say that's probably the reason why we don't have an overabundance that creates that destruction of what we have. If we didn't have all those extra elements, we would probably have a free fall into a pit. But that shows us, if that's possible, one of the ways that we can basically make sure that star travel can be maintained sustainably in space, if we know how to reprocess all our materials using these little tricks. We just have to basically figure out how the Earth has done it to make sure that we're using the most efficient means rather than what everybody thinks is going on.
Sure. And also, I would like to add the other thing is, if you have a salt solution, now your liquid is conductive and offers a path to short out any excitons that form.
Right.
So just another step in the process. But yeah, I mean, you're still going to have higher reaction rates, because a lot of these have a really good band gap, but they have poor adsorption properties, even though they have a good long exciton lifetime. So really, the only thing driving that absorption that you have remaining to try is temperature and heat, temperature and pressure. So,
Right.
I mean, graphitic carbon nitride really doesn't have a problem with adsorption rates, though. But I think the lifetime of the exciton is just short. But then you can modify it with heterostructures, and I've seen cobalt tetroxide work really well, but cobalt is pretty rare.
I've heard of people using ferric chloride too. They'll rebake the graphitic carbon nitride with that to basically dope it either with the iron or the chlorine to basically improve its photocatalytic properties. So
excuse me, I'd like to share something. It's a paper that just recently came out, and basically what it's called, factoring in gravitomagnetism could do away with dark matter. Observations of galactic rotation curves gives one of the strongest lines of evidence pointing towards the existence of dark matter, a non-baryonic form of matter that makes up an estimated 85% of the matter in the observable universe. Current assessments of galactic rotation curves are based upon a framework of Newtonian accounts of gravity. A new paper published in EPJC by Gerson Ludwig, National Institute for Space Research, Brazil, suggests that if this is substituted with a general relativity-based model, the need to recourse to dark matter is relieved, replaced by the effects of gravitomagnetism. The main role of dark matter, Ludwig points out in the paper, has historically been to resolve the disparity between astrophysical observations and current theories of gravity. Put simply, if baryonic matter, the form of matter we see all around us every day, which is made up of protons, neutrons, and electrons, is the only form of matter, then there shouldn't be enough gravitational force to prevent galaxies from flying apart. By just disregarding general relativistic corrections to Newtonian gravity arising from mass currents, and by neglecting these mass currents, Ludwig asserts these models also miss significant modifications to rotational curves, the orbital speeds of visible stars, and gas plotted against their radial distance from their galaxy center. This is because of an effect in general relativity not present in Newton's theory of gravity, frame dragging, or the Lenz-Thirring effect. This effect arises when a massive rotating object like a star or a black hole drags the very fabric of space-time along with it, in turn giving rise to a gravitomagnetic field. In this paper, Ludwig presents a new model for rotational curves of galaxies, which is in agreement with previous efforts involving general relativity. The researcher demonstrates that even though the effects of gravitomatic fields are weak, factoring them into models alleviates the difference between theories of gravity and observed rotational curves, eliminating the need for dark matter. So I invite you guys to follow the link and read the paper. Thanks.
Thanks. Thank you. Yeah, we'll take a look.
I'm actually kind of wondering that you mentioned the spin of the galactic spin. If anyone has considered that the reason why we don't see hardly any antimatter is because of a Coriolis effect from the universe itself rotating, and that, you know, if you were to like achieve a point of reference from the opposite hemisphere, maybe you'd find the majority of the material would be antimatter rather than matter. So kind of how cyclones and hurricanes spin one direction or the other, depending on which hemisphere they're on, as well as the rotation of the Earth, for the most part, controlling which direction they flow. Whenever they form, they tend to always move from east to west, as well as moving from hemisphere toward the pole. So,
would you need antimatter if you had anti-gravity?
well, I'm not talking about a need for it. I'm just wondering if that might have some effect to it, because if the universe itself is rotating, it would definitely have to be taken into account for any kind of star travel. We'd need to know where its universe center is, as well as the direction of spin, and if it's drifting, what direction it's drifting to, in order to account for longer range travel, especially between galactic spires. So, and it could affect every experiment someone's doing if they're not accounting for that too, giving them a bunch of random noise. They can't figure out why they're not getting an accurate measurement too. Sorry, I just had to get that last bit in.
So it would have an intrinsic spin to it. Is that what you're suggesting?
Well, I'm not saying it does or doesn't. I'm saying that it's something I haven't heard of anybody looking into. So it may be something we may need eventually to look into in order to kind of finalize and get rid of a lot of the need for fudge numbers in mathematics, where we do the testing and then we take the results and apply our answers to those numbers. We're not sure what the right answer would be or the right input would be, and adjust those numbers, and constantly having to adjust those. For one thing, if we have a frequency that the entire universe is vibrating at, and that frequency is drifting, which accounts for our temporal movement, when you cross a barrier where there's something in your experiment where it's effectively matching that frequency, that would cause some random noise. You wouldn't have any idea what it was from, unless you have like an extra universal frame of reference, or you have enough information on how the universe is actually functioning and aren't completely ignorant of like things like, you know, universal rotation and whatnot, and how it could affect you. Once you have that, though, then it makes it a lot easier to go, oh, well, that's probably because of this, and that's probably because of that. And then you can start weeding through all the noise to get the true results you're looking for, so that they're not making it difficult to get your end result.
I can answer this. I can answer this question definitively if Tim would let me share my screen for a minute.
Well, may I mention something? The thing is, what do you mean by universal rotation? Because if you're thinking of like a reference frame of the vacuum, that's been shown by the Michelson and Morley effect not to exist. But well, yeah, I mean, Eric, go on.
Can I share my screen, Tim?
I don't know.
Is he there?
I don't think he's there.
All right. Well, let me just let me share my screen here.
Well, we're waiting.
Did somebody call for me, or did I misinterpret that? I was in the other room. I'm sorry.
No, nobody called for you, Jeremy.
I think Tim. Anyways,
Here we
I
go.
would like to add a little anecdote, though. After the Michelson-Morley thing happened, and we assumed that, then people started assuming that the vacuum had no material properties since it didn't have a reference frame. But the variable speed of light models are, I mean, basically they consider a vacuum with material properties, but not necessarily a reference frame.
So, do you think that the vacuum is has a constant density in all regions of the universe, or do you think there's regions of the universe where space-time is denser and regions where space-time is less dense?
It depends on what you mean, because all of the observations will be consistent with curved space-time, because a variable refractive index model with matter also affected by the refractive index will just appear to us to be a constant speed of light, constant refractive index locally, because
So
we're just down too.
So
but at a distance, that's where it counts.
Would you think that when you say space-time, would it, in your mind, would you think of it like the sphere on the membrane, or would you think it as space-time looking different? I kind of look at it, space-time, as concentric shells. So the closer you get to the matter, the more time slows, for example, because you're closer.
Well, is my screen showing here?
Yeah, but it's really tiny print. Can hardly.
Is it really?
Yeah, it's too minuscule to read. There you go. That's a little better.
Is this better? I'm on a phone. It's the problem. Is this better? Can you read this?
Yeah, that's working for us. Don't go any bigger there, or we'll lose it.
Right. So Randall Mills has a theory of an oscillating universe that transitions from a minimum size where everything is matter, and then it transitions to a maximum size where all the matter converts to energy. And so the reason that the universe is neutral is because during the contraction phase, where we're in the expansion phase now. So the rate of expansion is proportional to the rate at which stars convert matter into energy. And so space-time expands for every 3 × 10⁻22 kilograms of matter that converts to energy. And that's actually drives the expansion of space-time and the acceleration of the expansion. So we're in the expansion phase. During the contraction phase, where that phase starts out where everything is energy, matter is formed by a neutron production pathway. So the reaction that occurs, so at the end of the expansion phase. When all matter has converted to energy, there are gamma rays and electron neutrinos left, and they form neutrons. And so that's the very first particle in the contracting universe. Then the neutrons beta decay to hydrogen, electron, antineutrino, and then the beta decay energy. And then you've got the electrons, binding with the hydrogen atoms to create hydrogen, and then you've got things coalescing, and basically it's a different. There's no Big Bang in this situation, and so the number of electrons exactly balances the number of protons. The universe is electrically neutral. The universe is oscillatory in matter, energy, and space-time, without the existence of antimatter due to conservation of spin of the electron neutrino and their relationship of particle production to space-time contraction. So when what that means is that when matter converts to when energy converts to matter, when an electron positron pair is formed, space-time will contract relativistically. So the metric changes from Minkowski to Schwarzschild during particle production. And so the same type of special relativistic correction that you get when a particle approaches the speed of c, when energy converts to matter and you get an electron positron pair, contract, and in a resonator cavity is formed, and the photon that creates the electron positron pair is trapped into the resonator cavity that becomes the particle. And the electric field of the photon induces the charge on the membrane of space that was contracted, and that's where the charge of the charged particle comes from. It's actually induced by the primordial photon that created the particle.
Eric,
and so all this
Eric,
happens in the particle production frame, which is the absolute frame. So it's the only frame that you can reference, that you have an absolute reference, because the speed of light is 0 in that frame. The light will the band stop filter will stop light, and it'll create the particle pair.
Eric, I got a simple question. Would you say that the universe has an inner and an outer event horizon?
Well, I think you were the one that was mentioning the spherical shape. So it's an R sphere. You know what an R sphere is? It's topology. So the universe is closed. So in this model, the universe is closed, but it has no boundary. So it's finite, but it has no boundary. So it expands into nothingness, but the amount of matter is finite. And when the universe,
if you go into the future, there's less neutrons, and as you go into the past, there's more neutrons.
well, remember, it's a cycle. So the arrow of time is running forward now, and
But when after it reaches the end of that, you say it turns around and goes the other way, right? It contracts.
That's right. When all of the matter in the universe converts to energy by natural processes, then the universe will then contract, and the arrow of time will reverse, and this neutron production pathway will take over, and matter will start to form according to that.
And so
according
we're
to
in
that
the
path.
expanding time frame. And so that means there's another time frame where it's contracting that we can't see because time
That's
is
correct.
reversed.
In fact, matter is created during the contraction phase when the arrow of time is pointed backwards and spontaneous chemical reactions cannot occur. So life cannot arise in the contraction phase. And so astronomers find celestial objects that are older than the universe, and they don't understand how that can be. Well, the reason is that they were created during the contraction phase before the arrow of time reversed. And so they were created, prior to time equals zero. At time equals zero, the universe is at its minimum size, its gravitational radius. And at that point, the first, the first decay will happen, or the first, the first conversion of matter into energy will happen, and the expansion will start driving itself. And so here's like, for instance, a plot of the temperature of the universe during the expansion phase. And so you see the universe gets starts out extremely hot and gets very, very cold. But he's derived all the cosmological equations for the radius of the universe, the power of the universe, Hubble's constant. I mean, every single cosmological unsolved problem he has solved. For instance, the power of the universe. So it's a 1 trillion year cycle, right? So the cycle is 1 trillion years, almost 1 trillion. So, and it goes back.
So what's the name of the theory? What do you call the theory?
This is the grand unified theory of classical physics.
And now, is it like, is this the same as the oscillating universe or whatever they call it? So you got a big bang and then you got a big crunch, essentially.
No, there's no big bang. It's an eternal universe that's always been there.
So it's just cycling around. It doesn't have a beginning or an end, correct?
It doesn't have a beginning or end. It has a beginning of the expansion phase and the beginning of the contraction phase. And it's a harmonic oscillator. And so there's a restoring force, literally a spring restoring force that causes the universe to start contracting again.
So it's cyclical. It's cyclical, you would say, right?
Yes.
So what's the period of the cycle?
Universe.
Are we talking trillion years? Is that what you said?
It's 1 trillion. It's 999 billion point some years, almost a trillion years.
Okay, and
this is really the key equation. This is the quotient of the universe. And so this equation here tells you that for every 3.22 times 10 to the 34 kilograms per second of matter converting to energy. So 3 times 10 to the 34 kilograms of matter convert to energy every second. So stars are burning and converting matter to energy. And that conversion causes space-time to expand. Remember, when a particle is created, space-time contracts. When a particle annihilates, space-time expands. And so what's driving the expansion of the universe are all the stars in the universe burning and converting mass into energy. And this is
there black holes in this universe?
Yes, at the center of every galaxy is a black hole.
Okay. And it's an interesting theory. So one question I have, we're talking about neutrons a little bit.
Yeah.
My understanding of that of neutrons are unstable when they're free. They decay into a proton, an electron, and a couple neutrinos. So
That's correct.
if you're when you're condensing, it's converting to neutrons. In that state, would those neutrons be stable? Have to be stable?
No, a free neutron is not stable. It decays.
No,
within
I'm not saying it's in our. So we're in an expanded. We're in the what you would call emergent cycle. We're in the emergent cycle, not in the contraction cycle, right?
Right. We're in the expansion.
Right. So, but I'm asking about in the contraction cycle. In order for this to work, wouldn't the neutrons have to become stable?
No.
You know what I'm saying? Because right now, as we're going expanding, free neutrons are unstable, right? So in our state, they have a lifetime.
That's correct. Yes.
Right. But I'm saying in the contracting stage, wouldn't that lifetime have to be longer or almost infinite?
Not at all, because that's what the end of the expansion phase. All of the energy in the universe is in the form of gamma rays and electron neutrinos, and the restoring force occurs, and this reaction here, the gamma ray plus the electron neutrino, in one step forms a neutron, and that can only occur in the contraction phase because of the thermodynamic requirements.
But it's saying it requires 0.7835 MeV too. You need to add some energy in.
Well, no, that's the beta decay. That's the beta decay. So the and the electron neutrino have the sufficient energy to create the neutron. Then what happens is that the neutron then decays, and it decays into hydrogen, an electron, antineutrino, and an optional energy. This energy is sometimes given to the electron, the beta particle, and then this beta particle will then combine with this hydrogen proton and form a hydrogen atom, and then matter will start to coalesce.
So that hydrogen atom is ion. It doesn't have an electron.
No, it doesn't. It's a hydrogen at
ion.
It's a proton. It's a proton, and this beta particle is an electron. And so that's the neutron production pathway that is the reason why the universe is neutral, and not full of antimatter. I was going to show you real quick the I don't know why I can't. I've got to do this way, but there should be a way to very quickly. I don't know why I can't do this, but
just be patient.
Yeah, I know, but I all right. So here's Mills. Here's Mills' propulsion mechanism. So in his model, the free electron is a two-dimensional particle. It's a membrane of charge, and the charge circulates in rings. And the truly free electron is flat, and it has no gravitational mass. So it has inertial mass, but no gravitational mass. And when a free electron combines with a proton and forms hydrogen, that's when it gains curvature and it gains gravitational mass. But when it's a free electron, it has no gravitational mass. And what that allows is that the free electron can absorb a photon, because remember the electron is a resonant cavity, and so it can absorb energy. And so when the electron absorbs the correct amount of energy, it turns into a sphere as if it were a bound electron in a hydrogen atom. But the current that's flowing around the surface of the electron, the supercurrent, is guided by the trapped photon that's inside the resonant cavity. And the photon is of such high energy that the electric field of the photon causes the current elements at the poles of the electron to circulate at almost the speed of light. And so if you plot the velocity of the current along the z-axis, it'll flare out at the poles. And so that creates a hyperbolic or a negative curvature. And so when the electron is in this state, it's called a pseudo-electron. And so it's a real electron, but it's got a negative space-time curvature. And so he's gone and derived the geometry and all the energies that are the resonance energies that are allowed to create these types of electrons. And everything's in force balance. And this is sort of what the normal vectors look like in terms of electric field on this negatively space-time curved electron. And so what happens is, and so the way you get propulsion out of this is these electrons are ejected away from massive bodies at a tremendous acceleration, because they're very, very, they have a very high amount of curvature. And the more energy you put into them, the higher the negative curvature they have. And so they may accelerate away from the Earth at like 1 trillion times the acceleration that any other object would. And so the way you get propulsion out of this is you convert the electron to a pseudo-electron so that its space-time curvature is negative. And then you accelerate the electron between capacitor plates such that the negative plate is in the direction that you want to move, and it's opposite the gravitational mass, like the Earth. And so the electron will be ejected away from the Earth gravitationally by virtue of the fact that it is negatively curved, whereas the Earth has positive curvature. And so that acceleration happens on a gravitational basis. And then when it happens in between capacitor plates that are mounted to the craft, the negative electron continues to be negative, but it's ejected toward the negative plate of the capacitor. And so it pushes the negative plate away while pulling the positive plate behind it, while the Earth is ejecting it at 1 trillion times the acceleration that it would normally have. And so essentially you get some incredible accelerations with this. And the gravitational power that is provided by just 200 amps of pseudo-electrons is around 9.4 gigawatts of gravitational energy or power, 9.4 gigajoules. And so this is running continuously. And so it doesn't take very much energy to get some really astounding accelerations. So here's the free electron that I was talking about, when it's free, it's two-dimensional, right? And so there it is on its side, and the density of current is highest in the center, and the radius shrinks the faster it moves. And so a free electron that's traveling very fast will be will have a very small radius, and vice versa. And there's many ways. So you can collide these with gamma rays, or you can collide them with certain geometric structures that will also cause the resonance to happen. So trihydrogen is one molecule that has the right shape. And so there's different ways you can create these pseudo electrons. And his hypothesis is that the jets that are shot from black holes are probably pseudo electron jets. And you'd have to go through the book and understand why he hypothesizes that. But it's an amazing book. I would recommend it pretty much to anybody. And if you doubt it, I guess you can sort of look at what they just released. So they have a 250 kilowatt power source. That is pretty close to market. And this thing is only using water. It's using very, very small trace amounts of water. And it's a catalytic reaction. So hydrogen is fuel, and nascent HOH is the catalyst. And so this catalyst will bring the hydrogen down to a lower energy state below the ground state. And it's a stable state. And so the potential energy that's there stored in the atom is released when it's coaxed down to the lower energy state. And this is 250 kilowatts of power. Flash boiling and superheating water with probably a drop of water going into the reactor probably 5 seconds, is what I'm guessing. And this reactor is about a month away from going to market. It's a thermal reactor, so I think a lot of people are not paying attention to this company and to Brilliant Light Power. And I think a lot of people are going to get surprised when when some of these things start coming to market.
Hey, Eric, could you post a link on the chat for that company, please?
No, sure. So
Okay.
it's brilliantlightpower.com. And the book is I'll put the link for the book. But anyway, I think there's many more than one way to achieve propellantless propulsion, and this is just one of the ways.
Thanks.
Is everybody being so quiet?
No, I'm done. I was going to give a much longer presentation on this some other day, but I'm exhausted. my
Yeah.
voice is shot. So
I think we all
I hear you,
are.
bro.
Okay, well, it's been fun, folks. I think I'm going to sign off now and look forward to the next conference.
yes, it was great. I thank everybody.
It was fun.
I guess Tim is
Am
Probably
I?
napping.
Thanks, everyone. I am going to end the stream right there on on YouTube. Thanks for everyone who joined and everyone who donated to the super chats. We'll catch you on the next one, and of course during the week. I'm fucking ready to go and pass out. It's been 7 hours. There we go. I'm sorry. I'm tired.
Should maybe dedicate a time to talk about facility setup and whatnot, you know, like you were wanting to talk about before about getting a place together and setting up a lab and whatnot, you know.
I could talk that long about each one of the slides. There's like so much to talk about, but just an overview, I think, is more than enough for most people here.
Oh, yeah. All righty. Well, I'll catch you guys.
Regarding setting up a lab, we kind of have one already, but everyone's welcome to set up another lab.
Well, yeah, you need more than one lab. I mean, you guys can do the work you've got there, but there's no way I could make a journey all the way up there in order to work on something with you guys.
Hey, Mark,
There are people in my area that if I worked with them, then we could get something done here too. You know, it's that collaboration thing. So plus with mail and whatnot, if you don't have the tools to put something together where you're at, but somebody else has those tools, rather than hunting around to get the best you can find of something, you could maybe work with some other people to get exactly what you need because they already have the tools because they're working in a different area and their tooling would maybe make their ability to put something together specific for your needs rather than having to, you know, like I said, just try to make do with what you can get.
I shipped
Yeah,
out
it's very common in universities to share tools like that. In fact, I have the magnetic field meter that you guys accidentally broke. I have a working copy of that in case you want it.
Oh, you're talking about the that green one from China?
Yeah. Mm-hmm.
Oh yeah, we already got the replacement Pro, but it's not really that great of a tool. We got a better one from Alpha Labs. It costs like $600. But getting to what Tom was saying, yeah, we do share equipment and supplies between the labs and send stuff around. I actually just sent Jeremiah and Todd a care package, you know, with a whole bunch of stuff that they needed. And Jeremiah is going to be coming down to the lab like in 2 weeks. And oh, Jeremiah, did you get your package yet?
Yes, very exciting. Glad to see the CCTO. I was already slicing a hole in one of my hemispheres so I can cast that thing tonight. Because, you know, the second I got that in, I'm like, oh, man, that is immediately going to my vacuum chamber. Got to get that going. So I want to run that experiment. It's pretty exciting to actually run it with a super high K dielectric. And like what we already have with the Epoxicast 690 is pretty much one of the thinnest epoxies that you can get right off the market. And then I've got the epoxy thinner, which makes it even thinner. So I should be able to really cram a crap load of powder in there.
Awesome.
Hey, just remember that CCT
Package,
is,
powder.
it has high K only because it's a internal barrier layer capacitor. So it at high frequencies it won't work as well.
All right, that's totally fine. That's totally fine. It's
Right.
mainly about just adding the mass between those layers and having things, because these are fairly low frequency charging times, and it's mainly just about the total electric field that it can actually offer dipoles to orient into.
All right, you should be fine then.
Yep, that's what I'm hoping. We'll see.
Hey, Thomas Anderson, send me an email. We'll talk more material science sometime.
Okay.
You got?
Oh yeah, I'll save that and put it in the same email list that I got Jeremy's email in.
Cool.
So I'll say anybody that wants to send me an email, they're more than welcome. I'll drop my email in here too. So I think I put it in here last time. So hopefully those who wanted it already got it. But You might actually be able to get a hold of me through the Borg Steam Factory page that I've set up on Facebook, depending on if, I happen to have popped in at that point before you got a hold of me another way. So I don't hang out on Facebook as much as I used to. So format is just too difficult for my eyes now that they keep changing everything.
Well, good night. I'm headed out.
Yep.
Yeah, you know what? I'm gonna do the same. I gotta go take care of some stuff, so I will see you guys in the next meeting.
And I am back. Did everyone leave?
It's just eerily quiet. I believe that.
Oh, 1 second, 1 second. I lost. Okay, I can hear you now.
Yeah, it's just eerily quiet. That's all. No, nobody's really asking any questions or talking. This is actually one of those APECs. I think everyone's just exhausted. It was long, and we all got a chance to ask our questions, but quiet one afterwards.
Oh yeah,
Yeah.
I was actually for the first part of the presentation with Paul Violet. I was outside with a massive bonfire going on, and I was trying to melt the snow for the birthday party tomorrow. My daughter's having a birthday party, so I'm gonna have to rewatch that. Was there anything like good in his presentation?
Tell you the truth, I have to rewatch it too because I was busy trying to prep my presentation.
Oh, okay. Well, we'll both have to rewatch it. I know that Paul Violet is his knowledge in this field is very vast. He
Oh yeah, I totally agree, man. And we have a question for him too. I was supposed to ask him. I promised Nam I would. I didn't get a chance to ask him, but he's got this nifty little device with a cylinder inside of a cylinder, just like those caps we're building, only with a homogeneous dielectric, and in between those two cylinders, each of which have a slit in them to not block an eddy current or not create eddy currents as a closed shorted path, a solenoid magnet between them that pulses, and apparently the B flux traveling quickly and radiating its energy out through the electric field stored between those two capacitor plates produces some kind of force wave out one side. So it's a very interesting device that he's got in one of his documents, and I'd like to ask him about it. Ask him where the heck he got it from, and if he knows anything more about it. I'll have to send him an email, a picture of it, and ask him that way.
Hey, Mr. Anderson. I love those glasses.
This dude's cool, you know it.
These are just prescription glasses I put together with the stuff that I build my goggles at Borg Steam Factory with. They're way smaller than the ones I normally make whenever I make anything for anybody else. So
Jeremiah, check out the living room now. This is the living room of the guest house.
actually looks like a house now, man. And hey, that is a bad coaster, man. No kidding. That is sick. Love it.
Poster. It's like
I see a lack of cat hair.
That's not cat hair. That's pinky hair.
No,
Yeah.
so I said I see a lack of cat hair. That means you're obviously not trying to build a real anti-gravity device because I don't see any buttered toast or cats around there.
There's Pinky. She's the lab dog.
He thinks the dog will suffice. That's the trouble, Thomas. He thinks the dog will suffice. He just won't. He doesn't understand. The physics doesn't work on dogs.
No, it's cats, man. They're the ones that refuse to land any other way but their feet.
Now I get
We can inverse the butter thing, you know. keep it spinning.
I always wondered about that. If you put a piece of toast with the butter on top on the back of a cat, what happens?
I can say that if you take, let me see if I have some of this stuff around here. I've done this before.
Oh no, you never.
Oh, here we go. Here we go. This stuff right here. No, you don't need the toast. All you need is this stuff. You see this? This is a rubber cement contact tape, right? You put this on the pads of the cat's feet. The cat will hover above the ground because it will never land. It keeps refusing to put its feet on the ground. Just like. And it doesn't come off. If you take and roll it up and make a long like this is a piece of that stuff here. It's just basically that rubber cement rolled up into a tube, but you can stick it together against itself, and it's somewhat stretchy around and leave it wrapped around a cat. Oh my God, they go nuts. And people are like, oh, why are you so mean? But it's like, after you do something like that, within like 20, 30 minutes, when the cat comes back, it's its turn. It's just a game to the cat, you know. You're not really torturing the cat, you're playing with it.
Where's your printer set up?
Mine? It's actually through there. Wait, let me see here. Where's the settings on this thing? Oh, I've got it buried under the conversation. I had to split that off.
Oh, you're on a desktop?
Yeah. Okay. I'm gonna move that out of the way. Hopefully that won't fall over.
We see a different camera now.
Yeah. Yeah, it's free from the confines that the other one is on because I've got it mounted on my frame that all my stuff is sitting on. The big printer is sitting up there behind that box. So right now that plastic's kind of sitting in the way because that was my barrier between my chemistry setup I had over here to keep any fumes coming off it from coming into the house. That way it would get pulled up into the vent and vacuumed out. But it's, let me see here. Oh, there you go. You can see the top of it there. It doesn't have a head on it right now though, because I have a laser attached to the head. So rather than the router head that it came with. So the intent is eventually I'm going to combine all of that together. So that way I can switch between the laser head and you know, pretty much anything else that I need to basically work with. 3D printing head, laser for cutting or smoothing the 3D prints, and then the router for basically cutting harder materials that I can't quite print with yet. So, but.
What kind of laser do you have on it now?
It's a 2.5 watt 405 nanometer. So it's a lot more powerful than you would think. I did not think it was going to be capable of doing what the 15 watt blue laser does. But like the blue laser, when it's unfocused on a piece of MDF, it doesn't do anything to it, even at full power. Full 15 watts, it's just basically light, right? That UV laser that's back there, when it's fully unfocused to a 1/2 inch in diameter dot, even at 2.5 watts, that 2.5 watts in a 1/2 inch dot is still immediately starts smoking the MDF. It leaves charring and whatnot behind whenever it gets done. I took, while it was like not quite fully focused, took a piece of solder, rosin flux solder, and pushed it in underneath it, and like it melted like a 3/16 inch bead of enough to form a 3/16 inch bead of solder, and dropped it to the bed. So I would just say that, remember, if you're melting metals with it, don't take your eye protection off until you shut the laser off, because that bead is going to be sitting there refracting that light all over the place, and it left orange spots on my eyes for like 3 hours almost. So, which luckily, like I said, it was hitting a curved surface, so it was spreading out even more. But man,
Yeah. My buddy got hit in the eye with a UV 405 at 500 milliwatts. He has a permanent spiral in one of his eyes, directly in the center of his vision. So he looks at like a soda can from about 2 feet away, and if it says like COLA on it, he'll see the C and the A, and the O and the L will just be a swirl. So
Oh my God, is that your buddy?
damn.
yeah, that's him. Yep, he got hit. He got hit in the eye.
Shit, man.
Oh my God.
I feel. Oh my God, that's so bad.
As he quotes, he wanted to make it onto a T-shirt. The best light show you'll ever see once.
Once, yeah.
Oh my God, no.
Maybe you should have underneath there somewhere that says, "Do not look into laser with the remaining eye."
Yeah, that was also another one of his ideas he wanted to put on a T-shirt. So you got it. You got the right idea.
Good God, man.
I am more scared of afraid of Jeremiah's laser than the 100,000 volt power supply.
Quite honestly, so am I.
Yeah.
Especially when you hand it to somebody else. That's when I'm petrified.
Oh, I know it, man. That laser is potentially the worst, most dangerous idea that could have been made.
I have a whole box of laser protection goggles sitting up there that basically anytime I'm working with someone else, everyone has to be wearing it. You can't work in the room without it. I've also got a ton of like, what is it? I think it's 2326 acrylic. I'm not sure. It's basically just big sheets of, they're like 1/8 inch thick of like solid red transparent acrylic, meaning that the amount of red that can be added to it is at its maximum dopage. So you can't really make it any more solid of red without it starting to go into an opaque state. So
Sounds pretty effective.
Yeah, 2423. Oh yeah, it is. It is also actually really easy to cut this stuff though with the laser focused on it, because it absorbs all of it and converts it all into thermal energy. So I have found though the 455, this isn't actually as effective at blocking it as the orange that I've got. So kind of a curious little thing. Like it blocks it pretty well, but the orange not only completely blocks it, but it actually, if you shine the 455 laser on it, on one side, obviously you've got the blue going into it, but you'll see if you put a piece of paper up next to it on the other side and the light is in a straight beam, you'll see an orange dot form on the other side. So it's actually converting the light into an orange color by, phosphorescing, I guess, or something. Kind of like how, they pump, the DSSP lasers, like the YAG lasers and whatnot.
Similar. There's actually another technology that uses something very similar. It does use a 455 pump diode to strike a phosphorus target. And the idea behind their light source is that they can focus onto the phosphorus with such a fine point that effectively they can get incredibly low divergence, about 2 degrees or less, into a focused beam of fully white light from that conversion. So that's a pretty incredible phenomena, and they're just using 455s to pump it. It's one way to do it, but yeah, there's already applications of that in commercial products you can buy now. They're pretty fantastic.
Right. Have you guys considered, if you needed UV lasers too, of using old fluorescent tubes? Put together a fixture so you can
concentration of power. I mean, we need a lot of power in a very tiny space. That's
right. But what I'm saying is you can grab a hold of the ends of it and with a fixture so that you can trap what's inside of it and put a little XY system together in there to basically cut a hole in the end and then apply your lensing on the end. So that way you could have your half mirror on one end and full mirror on the other. And then when you charge it up like you normally do when you light up a fluorescent lamp, the gas inside is putting off this really high frequency UV. There's like I think it's 267 and 180, or maybe it's 257 and 180.
Yeah, it's 188 and 265, I think.
Okay, so basically you've got those frequencies to work with, which the 180 nanometer range is more than enough to get down to where you can start busting molecules that normally are very difficult to break, like carbon dioxide, so produce ozone, whatnot.
Right, but are you recommending trying to actually use a UV fluorescent tube as a source of focused light?
Right, because that's all they are, is you're activating the atoms inside with your constant pulsing of electrons running into it, like you do whenever you turn the light on to produce that white light. It's the UV light hitting the phosphor on the outside.
Just, all right, but I mean, you can just buy a regular UV sterilizer lamp that's that is exactly like a phosphorescent white fluorescent tube. Only difference being that it has a quartz.
It's not coated, right? Or it has a quartz tube. Yeah, I was gonna say, and it's not blocked.
Why buy something? Why do something?
But I'm not talking about using the lamp itself. I'm talking about using the ends.
What do you mean using the ends?
So you can get a straight beam coming out of the end from the light, the excitation of the gases.
The filament? Are you talking about like breaking?
No, you're removing that and moving it aside so you can actually extract the light straight through where that would normally come in, and you just basically charge from the edges of that, because you can just use a high voltage to fire that off. But that would still give you easier access to the gas in order to excite it than, trying to basically like wrap it or excite it with like an external high voltage power source, like a Tesla generator or something like that, So it's something that I'm looking into, just because they're everywhere. You can just go pick some up. In fact, a lot of places are basically throwing them away and trying to, like, out here they're throwing them away. I imagine if you're living back east, they're going and sending it to recyclers, because they won't let them just throw it away in the landfill. Out in Oklahoma, they don't give a crap though. Environment, what environment, So.
Huh.
But I mean, and I'm not saying that everyone should be doing this. I'm saying if you're having trouble coming up with resources, especially something that you can use and dispose of after you've done your testing, it's a possibility that something like that would be useful to produce that. So, like, I'm using an old CRT from a TV to build my vacuum chamber so that it's big enough and has the proper shape for an XY system, so I can put an actual CNC unit inside, like you have inside of a 3D printer, but in the vacuum chamber for my vapor deposition. So
yeah, we want to get into that too. We've been needing to do vapor depositing on quite a few surfaces, and we wanted to screw with bismuth as well, because bismuth, it's a really fantastic material. If you can get the layers just thin enough, then you start to exhibit really unusual properties.
Right. Yeah, that's why I was talking about the spin coating, where you just use a rod of it to coat it if you want to do quick testing without having to put together a vapor deposition system.
Spin testing. So what do you literally friction deposit the stuff on the surface, or what?
Right. You use the high friction and a little bit of pressure to basically push all the contaminants from between, like say a sheet of metal made of steel and your bismuth. So that way you get pure bismuth on steel without having to do like I did, where I took a 4 thousandths of an inch thick sheet of steel, and then just use a soldering iron, and I put rosin flux down first, and then I melted the bismuth directly onto it. So plenty of bismuth. That's only half of it, because I actually have a bunch of it. Like actually, now that I think about it, crap, I keep forgetting this thing is back there. That's all 75 micron sized bismuth powder.
Nice.
So, but
you can do some fun stuff for that.
I haven't even gone, like, it's 75 micron and smaller. I don't have anything to basically separate all the smaller particles to make sure they're only 75 microns. So, or I didn't at the time. I've got better screens now, but that was me taking that stuff and just basically hammering on that stuff with a piece of like steel water pipe with the pipe cap on the end inside of a larger piece of steel water pipe with the cap on the bottom of it to basically crush it up, and then putting it into the coffee grinders and running it. So it's a lot of work, and I will tell you right now, this is not useful for coating things, because now every single one of those pieces of bismuth has got oxygen stuck to it. So
I'm sure with enough heat you can probably clear it out.
Oh yeah. What I was doing was I was trying to basically plate the steel by putting it between two pieces of aluminum. They're, I don't know, I think like 1/8 of an inch thick, but just something I could put heavy pressure on either side of it, but it wouldn't, if it squeezed out, it wouldn't stick to the aluminum. And then set it on the stove while I had this powder spread out over this 2 steel plates in between that so that it would bond the two together. Didn't work. Instead, I ended up with this weird kind of Brillo pad like looking stuff made out of the bismuth. So it was kind of an interesting material, but it wasn't the result I was going for. So that's why I still have this in case I ever decide to use it for something else that I come across that I need it for, or someone else needs it, and then I can just mail it to them. That way they don't have to go through the process of sorting and sifting and grinding and pounding it up and whatnot.
Well, that may actually be a thing that I may try to inquire from you in the future, because I am working with those types of materials right now, and bismuth has been a hot topic of mine recently. So,
were you looking at the piezo material, like
no,
the PZT material for your the high K dielectric material too? Or was it something else?
Yeah, PZTs are one of the things I looked at, but I actually want to stay away from the PZTs primarily because I'm not looking for any mechanical stresses on the structural framework of the system, and because it's not actually necessary to have any mechanical expansion or contraction. If I can eliminate it, it'll be best.
Well, I was gonna say, what in the PZT would be the useful component to create that high K dielectric? Like, I know you were talking about titanium dioxide. And that's one of the components for making the PZT.
Well, yeah, no, I tried titanium dioxide as a test in earlier prototypes because it's super cheap off the shelf material as a dielectric, and you can mix it with whatever. So I used it mainly because it was cheap and because it was available, not because it was actually good or all that useful. And I can't wait to stop using it, basically, because now that I have the CCTO in from Falcon Space, I'm actually quite excited about mixing that stuff up since it has a significantly higher dielectric constant.
Wow, I don't know what happened to it. I've got a pound rod of zirconium around here.
Interesting.
Usually it's sticking out in the way. Well, a friend of mine in Texas and I are we're working with piezo elements. I'm more interested in thicker piezo elements and custom form in order to basically control the frequencies that I can produce, because I was looking into lipus. But zirconium oxide aerogels would be almost like the ultimate refractory material that you can get your hands on without spending a fortune, like say buying a bunch of tantalum and hafnium carbide to make an aerogel out of that. So it's better than basically aluminum oxide when it comes to its high melting point. So, but try buying some zirconium oxide bricks, just straight ones, and the only place you can find them is like China. There's nobody in America manufacturing or selling them, so, which is kind of odd, I'm not sure what that's about. Hair is like trying to attack me.
Availability of materials is a real pain. Like, there's some materials you just can't buy from the United States, and most of those, like being dielectrics and whatnot, there's just no way.
Oh, you were mixing titanium dioxide powder with something, weren't you?
That's correct.
Okay, that's why I was talking about the PZT material, because see, we're working on basically, making our own. You're basically looking at making a ceramic clay out of a lead oxide, titanium oxide, and the zirconium oxide. And if you skip on all those components and work just say with zirconium and titanium oxides to make a ceramic material, it could be fired out to make a solid block.
Well, yeah, if it can be fired out, that's great. But ultimately what I need is an extremely high insulating value dielectric, one that can withstand a huge amount of potential per millimeter of thickness. And generally that's going to be a ceramic manufacturing process that'll involve a binder that's then baked out. You'll probably have a shrinkage of about 15 to 30% on the total size of that actual press piece. So obviously the thicker you make it, the more complicated it gets, limiting the
I don't think it's the process is going to be that difficult if you're really wanting to do it, because I'm using a shortcut for what I'm doing of using basically sodium hydroxide to break these components I've got down and make a hydroxide formation and then extract the sodium afterwards, which I don't know why everyone keeps assuming that the only way to extract the sodium hydroxide from something like, say, aerogel, you're making aerogel, you dissolve glass or quartz or something with the sodium hydroxide, right? Then you have to basically extract that from the system, and then while it's still in a wet state, find a way to get the water out of it without the matrix collapsing.
You're talking about using water for this thing?
Well, that's what's normally done, right? But what I'm saying is, if you extract the sodium without an acid, an acidifier, if you use like an artificial acidifier, like an electrical potential, you can attract the sodium away from it through the solution. And if you have something to catch it so that it doesn't re-enter the solution, so that it becomes a part of the matrix again, you don't have to worry about that salt building up inside of your compound, and then you have to basically extract that before you can even start working and break your components up. Once you have a gel formation of these compounds, the amount of heat it takes to condense them into a solid ceramic is almost nothing compared to just working with the raw powders and whatnot and mixing them together and then trying to bake it. And the amount of heat that you would need, you might be able to get away with like a $300 kiln that only goes up to, like, say, 1200 degrees Celsius. So
And we do actually have one that already that goes up to 1200 degrees Celsius, exactly that. So we'll be already trying several variations. I don't think I want to use any salt mixtures. We're looking for some really high dielectric constants, and the reason I want to try cold first instead of having to sinter it is because it's a process that's replicatable by anybody, and we're going to see how well that works and measure how much charge we can store. But should we need to go to actually something that would be, truly on the industrial scale, there's going to be serious limits of trying to 3D print it or doing it by any other method than extremely high pressure commercial processes at high temperature, just because we want a material that has the complete structural properties with no other catalyst and no other breakdown agents or anything else that could possibly be left in there. Like there is 0% chance for anything to be added into there. If we use plastic binders, we don't deal with that problem. So think about it this way: you're putting 100,000 volts across something that's just a few millimeters thick. You can't have any imperfections whatsoever. And at this stage in the game, like maybe in the future, 3D printers will be able to do this, or maybe there will be a technology for it. But I think right now, that's just not really that viable of a possibility to get an equivalent material made by a different process than high temperature sintering and compression.
what was the reason for not using something like styrene or the Teflon or
Teflon is
polyethylene?
a low K, low mass dielectric. Those are fine because they're formable.
But they're on one half of the spectrum, and you need the other half, right?
Right, exactly. It's the other half that gets complicated, where you need something that actually can hold a huge amount of charge and also has a reasonably high amount of mass per volume. That's when you need real dielectrics, and ceramics offer that, because if you look at the molecule size of some of those materials, not only are they made of heavy atoms, but they're also very, very large clusters of atoms, so their density is pretty high. And you just don't get that with plastics. And with plastics, even at best, plastics maybe have a dielectric of 20 to 25, and you compare that to 200,000 of CCTO in the proper structural matrix, and it's night and day.
Right. I was going to say, I'd actually like to talk to you more about the the ionic lifters you were talking about?
I'll tell you anything you want to know about those, man. I have a stupid amount of time invested into those, and I've had some pretty remarkable results in terms of thrust to power ratio. And I've pretty much, I think, explained to you exactly what the mechanism of action is and the struggle that I've had in forms of optimizing it. Because I know exactly what I need to do.
Did you use any shape charging to like static shape charging with different materials to control it in a catalytic state rather than having to pump energy constantly into it? Something that constantly wants to return to the state that you want it in.
What you're talking about is a slightly different system. You're talking about more the TT ground state. I didn't want to add any mass. The systems that I was building were incredibly lightweight. We're talking like several grams to say, for example.
Oh, right.
Yeah, one of the thrusters I have here is 4 grams. It produces about 13.5 grams of force. Upwards.
Right. I'm looking at something to basically build a like a non-moving part drone.
Well, yeah, so am I. Exactly, but the way that I'm going to realistically do it is actually by extremely lightweight power supplies and extremely lightweight thrust modules that can produce a very large amount of thrust for their physical volume and for their weight ratio.
Right. Well, I got the idea from seeing the amount of wind that you were getting from your wand, because I never thought that the ionic wind thrust was really capable of going that high. I thought it was kind of weak. Most of the stuff I saw was all weak sauce compared to what you were able to do, even just with the wand, you know.
I got this little ionic air purifier we're screwing with. It's just got 6 grids inside of it, and I can stick that thing on a skateboard, and it'll push it along at a pretty good clip. Yeah, on a skateboard. And you know those things aren't exactly the most efficient growers. This thing produces stupid amounts of thrust. You can get like people as Franklin who was saying earlier. Well, these lifters, they just launch right off the table. I'm like, dude, my lifters will launch right off the table and rip off their wires and disconnect themselves from the power supply and still have momentum to boot on top.
Right, but there's, like you were saying, there's no air in space to be moving around, which isn't true. There's just a lot less. You'd have to hell of a lot more ionic thrust in order to make any use of the material that's in deep space. Because what, 2 atoms per cubic meter?
Right, exactly. But you can't count on that when you want to. If you want a continuous, decent acceleration from here to Alpha Centauri, that's not the way to do it.
Right. So.
And so I don't want to waste my time for that with in-space propulsion. Now, I love ionic propulsion as a technology, and I'll talk about it all day long.
That's why I said a localized technology for, say, you know, like if I were wanting to send something to you and I don't want to rely on the mail because they might actually confiscate it, start monkeying around with it to try to figure out what it is and then assume that it's like a weapon or something. If I can put it on a drone that I can basically just, you know, plot a course and make sure that it's got nothing in the path between me and you, it, you know, might take a while to get there, but it gets there and drops off the package and comes back, especially if it has a way of generating its own power source or replenishing its own power source. It just needs to stop periodically and let it build up charge again before it takes off, you know. So
you're talking
I have to do some more
there, man. I mean, we were talking about then dealing with the electrets and having super high density materials that have a stupid amount of electrical gradient, extremely electronegative, extremely electropositive materials.
That's why this morning when I woke up, I was thinking, man, what if I could basically make some modifications to surfactants so that instead of the typical ends that it has, one end has something with like a, you know, a high negative charge, and the other has a high positive charge, like say sodium on one end and fluorine on the other.
Just as what, like a surfactant
self-aligning, so that way,
or what?
Huh?
Is a surfactant liquid dipole or what?
Right. So that way, when you put them on a surface, they automatically self-align, so that whatever you're laying them on, one of those ends will affix to and form like a what do you call it? A forest of them attached with the other pole sticking up on the other end.
The funny thing about that is almost all dielectric ceramics do the same thing anyways, because they're already large dipoles. That's specifically what they're supposed to do. And that's why when they make these ceramic capacitors, they pre-align that dielectric by slamming it with an electric field before it's fully sintered so that it aligns with dielectric dipoles. Yeah, so yeah, all ceramics do the same thing of the other material. There's lots of ways to do it, I suppose.
Right. Well, like I said, you know, I was thinking about that because initially I was thinking that, you know, if your cavity you're working with to create your ionic wind through it is made of differing materials so that you can create a crunch at some point and a controlled vector for it it's not physically coming into contact with it. You're using a static charge to create your nozzle shape.
Well, I can answer
that way,
that.
All of your energy is being forced in the direction you want instead of it spreading out, you know?
Well, right, exactly. In this case, you don't actually use different materials. Those end up being heavier and creating complexities in the manufacturing and construction of the thruster. In this case, you just use electric fields to control everything.
What would you look at putting your building your body then for structural support out of?
In a real craft that was actually commercial in application, I have no idea, but my guess is
just something small.
Yeah, for prototype craft, honestly, right now I'm just working with balsa wood because it's cheap, easy, and I can put it together with cyanoacrylate.
Right. That's why I'm looking at you know, the friction welding for aluminum, so I can basically build it out of sheets of aluminum. So I do a lot of metal forming to basically make, you know, virtually everything. Like these are made out of sheet metal; they're just brass. So, you know, it's the formation I don't think would be a problem at all. It'd just be a matter of taking a model and pepper-currying it, basically.
Well, the weight would be a problem though right now. I mean, the power to weight ratio is just, it's good right now dealing with balsa and thin foils. Like I will use aluminum that's about 0.003 millimeters thick.
So basically carrying a 10 kilo package along with that isn't going to really fly.
Not at this point.
In the quite literal punny sense.
Yeah, not at this point in the technology. Now, theoretically, it is possible for it to carry easily that much in a small thruster design, It's just that right now it's extremely difficult for us to control the ions and exactly where they go. Now, here's the problem. If you create the ions via a corona wire in the electric field that you use to accelerate them to produce your reaction force, those ions are going to start out being produced by the corona wire and immediately start accelerating towards the collection grid with the opposite polarity. The problem with that is they're going to accelerate to a high velocity pretty quickly being in such a strong electric field, and they're not going to have very many neutral air impacts, therefore limiting the amount of maximum thrust that they can deliver, or basically the conversion of their momentum into the reaction momentum, which ultimately they're pushing against. So in order to get maximum thrust, what you need to do is create the ions outside of the acceleration chamber, which we would call a thruster part, and you need to pump them in via some kind of tube or vent or duct or something
kind of like electrically charging fuel and negatively and then positively charging the oxygen, so that when it combusts in the chamber,
right. Yeah,
it's going to slam together at a high rate.
Well, yeah,
pass it through a chamber that's got a charge on it too, so that way basically as it's
other way around,
the nozzle squeezes it even harder.
Other way around, Thomas. In this case, you actually want it to not hit as hard. You want the ions to enter and be accelerated as slowly as possible so that they hit the highest number of neutral air molecules. You don't want them to accelerate quickly, otherwise they'll miss. So you inject a very high concentration of ions into an acceleration grid that doesn't have a huge amount of acceleration voltage across it, but consequently you'll have to supply a slightly higher current. But as a result, the number of ions per million neutral air molecules is going to be significantly higher. That ratio will be higher. So you'll get a huge amount of thrust out of a very small package.
Right. Well, that's why I was thinking initially, like if you could create a static charge on your nozzle that the expansion is occurring in, and a negative charge, say on the nozzle, and a negative charge on all of the components that are being combusted, without neutralizing the combustion capability when it expands from the combustion, you should get an ionic squeeze to increase the speed that it's exiting, rather than just the normal combustion expansion rate that you get with like a rocket.
I don't get is you're using the word combustion. There's no combustion at all in the system.
No, I'm talking about for like a rocket. If you actually had two fuels you were burning, and normally like say SpaceX, they're counting on these two fuels when they combust. They create a fast expansion rate, which only has one direction to go, and that's out the nozzle, and that creates a thrust forward. What I'm talking about is adding an ionic potential to it, so that way it's the nozzle is pushing it out even harder than just the normal expansion. It's not just intimate contact with a solid mass that causes it to run in a specific direction as it's trying to expand.
Yeah,
you see what I mean?
That you can do. Yeah, I understand what you're talking about. And this is a study that I'm trying to remember who the hell did it. The amount of, if I'm remembering correctly from the study, the amount of energy that you actually need to pump in versus the amount of energy that's being expelled out there in terms of the mass is tremendous. Like just to generate the onboard power to ionize that much mass, it's exiting at that velocity is pretty huge. And so basically you need to find a way to use that burning fuel in order to generate the differential in charge itself, so that you can dream of supplying the power.
Right. Well, and that's why I said like using catalytic components that have like positive and negative charges naturally on their own. So as the stuff is coming through, it's basically creating an electron disparity that flows back to the direction that you want it to go to in order to create the massive voltage necessary to basically create the extra thrust when it's dumped to the nozzle.
Well, your rocket would certainly, I mean, if you're pumping out charge from the end of the rocket and you were charging up the body of the rocket closer and closer and closer to the polarity of the Earth, I mean, you would basically just shoot yourself up into the Earth through electrostatic repulsion and through whatever force that you had. So you'd be a lot more efficient getting up there if you did have a way to just jack out a whole bunch of charge.
Obviously, something we need in rocket propulsion too, because only 1% of the rocket is payload. The rest is all fuel and body, you know.
I'm sorry for interrupting, guys. I still have it recording. Is it okay to put this material online, or?
I don't care. I don't know what Jeremiah has to say.
Okay, well, cool. Okay, yeah, I just wasn't sure. Sorry, I'm just making dinner and feeding them puppy dogs. So, okay, well, yeah, I'll cruise back out. Thanks again, guys. I'll just leave it running. So,
yeah, I'm gonna head out of here, guys. Take it easy. I've gotta probably eat something here.
Oh,
yeah. Well, if you get a chance, I guess message me, Jeremiah, and we can talk more about the ionic stuff, because I really am interested in that. I'd kind of like to know if you thought any further too on like the idea of using the two materials to generate a static charge, like I was doing, and a way to collect it and whatnot. So
I'll be honest, I haven't, and the main reason is because the power dissipation required. I can't fathom those materials realistically having much of a percentage of contribution, considering I'm pumping 30 or 40 watts into some of these systems. It's just that amount of power being generated by something like that is so far out the scope. I'm not sure if it's necessary to add the weight that it would require.
Well, I mean, but from the power generation process I was talking about with the urethane and the styrene, which better materials would be something like Teflon and foam urethane. They have a much bigger disparity between the two of positive and negative triboelectric charge potential. So
do you think there's actually a way to produce any kind of extra power out of that system just by pumping airflow through it, or what?
I wasn't pumping flow through it or anything, and it was still generating a measurable charge. The voltage would continue to go up as long as I was testing and didn't discharge the material. I was just testing the ohms on it, but when you flip it over to the amps it's producing, it's like very, very negligible, like maybe 5 milliamps. But again, it's just two pieces of paper painted with some material. I didn't electrostatically charge it to create an electric effect on it or anything else. Just mixed a little bit of graphite that I ground up into it in order to try to spread out the conductive like feelers across it, kind of like you do with a solar cell, where you've got those little filaments on the surface to try to collect electric charge on that side, rather than just trying to tap to one corner of it and expect it all to flow to that corner. So
clever. Yeah, we should talk. We definitely should talk. I think I was going to send you an email. I believe I lost it last time. Can you just shoot me one over just for the sake of I gotta jump off here. Can you shoot me one at exoticpropulsion@gmail.com?
Exotic propulsion?
Yeah.
Okay. I'll try to remember that. If you drop it in the chat though, I can just copy and paste it.
Yeah, I will do that. Anyone else who wants it to.
So I don't know who I talked to originally, like with the Google Drive. Was that you that sent me an email there?
That would have probably been Sean.
Sean, okay. All right, yeah, I'll email you. So
awesome, man. All right, guys. Well, everyone, take it easy. For those who are left in here, y'all have a good night.
You too.